On November 9th, we recorded what might be the most astonishing footage of 3I Atlas yet, showing vast jets of material stretching millions of kilometers into the void of space. In this video, we'll dive into Avi Loeb's new analysis of those images and the strange mathematical problem behind them. Because, according to the data, this object seems to be shedding far more material than it should even physically be able to lose. The jets facing the Sun extend roughly 1 million kilometers, while those directed away from it reach nearly 3 million kilometers into space. To put that into perspective, the distance between Earth and the Moon is about 400,000 kilometers. These jets stretch 7 times farther than that. Even more incredible, back in July, the Hubble Space Telescope observed this same object surrounded by a faint, glowing halo. But now, the new jets captured on November 9th are roughly 3,000 times larger than what Hubble saw. 3,000 times bigger in just a few months. That's almost unthinkable. Normally, comets develop a single main tail pointing away from the Sun, a result of the solar wind, a constant stream of charged particles blowing at over 800,000 miles per hour. So to see jets actually pointing toward the Sun, pushing against that powerful wind, is extremely unusual. For them to hold together for over 1 million kilometers, they must be unbelievably dense and powerful.
Now, anti-tails, jets pointing toward the Sun, do occur naturally, but very rarely. For example, in 1992, astronomers found that comet Shoemaker-Levy 9 had passed too close to Jupiter. The planet's massive gravity tore it apart into 21 separate pieces. When those fragments crashed into Jupiter in July 1994, each created explosions so huge they were visible from Earth. The impact scars were larger than our entire planet and remained for months. Another case was Comet Holmes in 2007, which suddenly flared up, releasing an enormous expanding cloud. Both events were natural fragmentation, comets breaking apart. And that's likely what we're witnessing with 3I ATLS right now. A comet shattering into many fragments, each producing its own jet of dust and gas. But here's where things get even stranger. Avi Loeb ran the numbers, calculating how much material those jets must be ejecting, and the result is staggering. He estimates that 3I ATLS is losing around 50 billion tons of material every month. Now, scientists estimate the entire comet's total mass at about 33 billion tons. Let's be clear, total weight, 33 billion tons. Material lost per month, 50 billion tons. It shouldn't be possible to lose more than your total mass. In short, the math doesn't add up. But this kind of paradox isn't entirely new. When Shoemaker-Levy 9 broke apart near Jupiter, the total mass of the debris far exceeded initial estimates of the comet's size. That made sense once scientists realized it had completely fragmented. When the Sun heats up an icy object, the surface doesn't melt evenly. The side facing the Sun warms rapidly, while the opposite side remains cold. That temperature difference creates internal stress that can build until the entire structure shatters like glass under pressure. When it breaks into smaller pieces, the total exposed surface area skyrockets, allowing more ice to vaporize at once. That leads to more jets, more gas, and more visible activity. So if 3I ATLS has fractured into hundreds or even thousands of fragments, That could easily explain the 7 massive jets observed on November 8th and the enormous plumes seen the next day, each fragment producing its own stream. All those jets combined could match the enormous material loss Loeb calculated.
But here's the twist. We still don't know for sure if 3II Atlas has actually broken apart. If future observations reveal that it's still a single, solid object producing these immense, high-speed jets, then we're looking at something completely unprecedented, the first of its kind. Because, by the laws of physics, no solid body should be able to lose more mass than it has. There's also another mystery. 3I Atlas is traveling in what's called a retrograde orbit. If you look down at our solar system from above the North Pole, you'd see that every planet orbits the Sun counterclockwise. Earth, Mars, Jupiter, all of them. But 3II Atlas is moving clockwise, the opposite direction. Only about 1 to 2% of known objects do this, and most are small captured moons, not massive interstellar visitors. Even more peculiar, its trajectory lies almost perfectly along the ecliptic plane, the flat disk where all the planets orbit. Imagine our solar system as a flat plate. Most interstellar objects approach from random angles, above or below that plate, but 3II Atlas came in almost exactly aligned with it. The odds of that happening by chance? About 0.2%, a 1 in 500 coincidence. We've seen something vaguely similar before, Oumuamua, the first known interstellar object. It behaved in bizarre ways, an odd flattened shape, unpredictable brightness changes, and even unexplained acceleration as it exited the solar system. Avi Loeb famously proposed that it could be an artificial light sail, like a massive solar panel pushed by sunlight. Most scientists disagree, suggesting it was a natural comet made of hydrogen or nitrogen ice, but the mystery remains. The difference is, Oumuamua was tiny, only a few hundred feet long. 3II Atlas, on the other hand, is over a mile wide and weighs billions of tons. Finding something that large traveling backward through the solar system is highly unusual. And when you combine that with the impossible mass loss rates seen in November's images, you get one of the most extraordinary enigmas astronomers have ever encountered. If you enjoyed this breakdown, don't forget to like and subscribe, because the story of 3II Atlas is far from over.